so we're going to illustrate some of the things that we just derived for simple harmonic motion. Remember, we're using as a demo of simple harmonic motion a mass on a spring, but this is applicable to any time that you have harmonic motion, simple harmonic motion. And all you need for that is to have the restoring force be in the opposite direction of the displacement, and the restoring force be proportional to the size of the displacement. So in other words, if you displace this twice as much, the restoring force is twice as much, but in the opposite direction of the displacement. So it's not only applicable to a mass on a spring, but a whole lot of other physical situations. This is just a convenient one to illustrate in the lab. But it applies to molecules, for example. When you have two atoms with a molecular bond between them, that's like having a little spring between them. If you pull them apart, the restoring force wants to pull them back together again, and that force is proportional to how much you displace it by. So simple harmonic motion is important for a whole lot of physical examples. So let's use this one to illustrate. So when we analyze the equations of motion for a simple harmonic oscillator, we found that the period of it is 2 pi times the square root of the mass divided by the spring constant. So T is proportional to square root of m, the mass, divided by k, the spring constant. This spring is the same spring we used in the previous demo, and we derived the spring constant for it. So we actually know what it is. So what we're going to do here is illustrate the period with a 200 gram mass, and then we'll double the mass, bring it up to 400 kilograms. We'll measure the period again and see that it's increased, like the square root of 2, or a factor of 1.4. So first let's measure the period. Now the period here is pretty quick, it's almost a second. Too hard for me to catch it with my stopwatch. So instead we're going to watch 10 periods. So we'll displace the mass, we'll let it go up and down, one full motion, that's 1 period. We'll do 10. So 1, 2, 3, 4, all the way to 10. Then we'll take a look at how many seconds that took. Then we'll switch masses, increase mass, and see if we get an increase in the period. Okay. All right, so we displace it, and remember, it doesn't matter, the period does not care whether I displace it just a centimeter or 5 centimeters or go all the way down to the ground here. It's going to have the same period. Okay, so I'll give you something nice and reasonable here. Ready? Set. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that was exactly 10.00 seconds. So this mass on a spring has a period of 10 seconds divided by 10, or 1 second. All right, cool. Ding, ding, ding. Okay. Now, let's switch masses here. We'll add some more mass and double up the mass. So now we have two 200 kilogram weights. And of course, you saw that now the displacement is bigger. We've got more mass, more x there, more displacement. All right, so I'll perturb it from equilibrium again, and let's start from scratch on the stopwatch, and we'll measure the period, again for 10 periods, and we should get a larger number by the square root of 2. So 10 times 1, the square root of 2 would be 10 times 1.4, or we should get about 14 seconds. Ready? Oops, start from scratch again. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 13.5 seconds. Not bad. All right, so that illustrates how the period changes with the mass. Again, if I had a different spring with a different spring constant, we could play around with that and see that if you increase k, because k is in the denominator for the period, you would get a period that's slower. Okay? Think about it this way, a stronger spring, right? Higher k value, it's just going to move slower. Okay. What other things could I illustrate here? Well, you could illustrate the fact that it doesn't matter if I pull this down a little bit or a lot, we get the same period. So how about if we pull it a lot? It should take about 1 second to go back down. Here, we'll try it again. Ready? 1, 2, 3, so it doesn't matter. We just pull it down a little bit. We'll just do like 2 centimeters just so you can barely see. 1, 2, 3. Doesn't matter. The amplitude I give it doesn't affect the period at all. This period just depends on the mass and the spring constant. Okay. All right. Thanks for watching. On to the next demo.